Hello everyone. So this is a very short video to demonstrate after AWR simulation how can we plot results on a Smith chart. And this will be very useful for our homework number 3 for modern radar circuits and systems. But before I formally get started, let me use 1 minute to summarize what we have done recently. So we have learned Smith chart, that's for sure. We have also learned impedance matching. If you want, so basically we have covered the 2 lectures with a few exercises in our classroom. But if you want to do more exercise, which is actually strongly recommended, please look at lecture number 10 notes. So this is also uploaded to Blackboard. So basically in lecture number 2, we have quite a few examples of using Smith chart and doing impedance matching design. And for today's demonstration, I'm going to use one of the examples to show how to plot the results on Smith chart. And I also want to mention that when we learned impedance matching, for example, when we learned the L-match network, this kind of L-match network design, we actually covered pretty much everything, like how do we move from, for example, point number 1 to point number 2, and then down to point number 4. Basically, from 1 to 2, we have to add a parallel inductor because the upper region is inductive, and from 2 to 4, we have to add a series capacitor. That's for sure, right? The only thing we didn't mention clearly is how do you determine the size of the components, the impedance of the inductor and capacitor. So to do that, it's actually quite simple. For example, I'm right here on page number 9 of lecture 10 notes. We have already shown that at point number 1, you can read out the admittance. You can also read out the admittance and impedance for point number 2, as well as the impedance at point number 4, right? So when we move from 1 to 2, we add this parallel inductor, and basically the admittance of the inductor will be the difference between the admittance of y1 and y2, which means the admittance at point number 1 and point number 2. So you calculate the difference on the admittance. That's going to be the value for the parallel inductor. Pretty simple. And for the capacitor, because the capacitor is responsible for the move from point number 2 to point number 4, then you compare the difference. You read out the impedance at point number 2 and point number 4 on Smith chart, and then calculate the difference. And the difference is going to be the impedance value of the capacitor, right? And the only thing I want to emphasize is those values are actually normalized value. So if in real problem solving or in exams, you are required to figure out, if you are required to figure out the true component value, you have to normalize it back, right? Consider the 50 ohm, okay? So that's pretty much what I want to mention before our demonstration. So for the demonstration of Smith charts plot in AWR, let's use this example. Example number 5 of lecture number 10. Basically, this example, we have to design this shunt stub transmission line match network. And in our class, we have already covered, you can use Smith chart. You start from the impedance point, rotate by 180 degree, get the admittance point. Then the first section of the transmission line, L1, will be responsible for the movement from here to there along the constant reflection coefficient circle, right? And the second transmission line, L2, the shunt stub, will be responsible for the move from this point number 3 to point number 4. Basically, we are adding a shunt inductive component so that we cancel out the imaginary part and then move back to the center of the Smith chart. All right, so those we have covered, and now what we are going to do is to run AWR simulation to confirm our solution is correct. So I'm gonna bring up my my computer, bring up the Windows environment, open AWR design environment. Okay, and this is for educational purpose only. And in our project, I'm gonna create the same schematic first, right? So I'll go to project, add a schematic, new schematic, name it as, let's say T9 matching. Okay, and there I'm gonna add. If we look at the schematic, I have a resistor in series with a capacitor. Then I need one transmission line and another shunt transmission line. So let's go to elements, look at passive. Let's see, where is my passive component? Oh, lumped element. All right. Lumped element, we have a capacitor. I drag this cap into the schematic, right click, rotate it, and the capacitance value is 0.995 picofarad. So I'm gonna change this to 0.995 picofarad, right? Okay, and I need a resistor. So I drag an ideal resistor into the schematic, rotate it, and assign a value of 60 ohm. And now I need transmission line, and for the simplest simulation we can use ideal transmission line model, specify the parameter by phase. Okay, drag this transmission line into the schematic and make a connection like that. And our problem is specified at 2 gigahertz. So I'm gonna specify the frequency as 2 gigahertz. Okay, and now I have to determine the length of the transmission line. Based on our manual analysis, the length of L1 should be 0.11 lambda, 0.11 lambda. So let's convert 0.11 lambda into degrees. 1 lambda is 360 degree, so 0.11 lambda is 39.6 degree. So this is 39.6 degree. And I'm gonna copy this, rotate it. This is a shunt stub, right? And we're gonna make a connection like that. The shunt stub will be grounded on the other terminal. So let's see, yeah, the shunt stub is grounded here, right here, okay? So we're gonna ground that, and the capacitor will also be grounded for sure, okay? Full screen display, and I have to figure out what's gonna be the L2 value, and from our hand analysis, the length is 0.095 lambda. So we have 0.095 lambda, convert it into degree, that's 34.2 degrees. 34.2 degree. All right. After that, I'm gonna add this port and set up my simulation frequency. So go to option, project option, do a single point simulation at 2 gigahertz. Remember to click apply. After that, what's next? The next is gonna be create a graph, right? So I go to project tab right here, right click on the graph, new graph, and I'm gonna do T9 matching graph, and you can name it whatever you want. And this time we're gonna check out the value on Smith chart. So I'll select Smith chart, click create. From the graph, we have to add a measurement. So for this measurement, we're gonna do linear port parameter measurement for S parameter, right? And we're gonna do a simulation for our T-line matching schematic. Okay, make sure this name is the same as the name of your schematic. We only have one port, that's port number 1, so this we don't have to change. And we're gonna plot it on the Smith chart, use complex version, so click OK. After that, I'll do a simulation. All right, great. So after the simulation, as we can see, we are right at the center of the Smith chart, which means we have perfect matching. And you can also do graph, add a marker here, okay? And this marker tells us it's actually very, very close to the center. It's only some numerical error when we did the calculation, right? And another thing you may want to try is, let's see if we are lucky or not. So I'm gonna move this port directly to the load and see if this time we can still get to the center of the Smith chart. So run simulation, and after that, as we can see, now we are not at the center of the Smith chart, and this point also matches very well with our hand analysis. Our hand analysis is that the load impedance, if we only look at the load impedance is 1.2 minus j times 1.6, right? And here it says 1.2 for the real part, and for imaginary part, almost negative 1.6. And again, this is a small numerical error, all right? And the numerical error actually was created when I did the hand analysis. So the result here is much more accurate, all right? So now I'm gonna move it back to our situation after match network is added, and we can see a very nice matching achieved. Run the simulation again, look at the result. It's at the center of the Smith chart. Okay, great. So another thing I want to demo, maybe just mention at this time, is actually you can tune those parameters. So AWR is a very powerful tool. Let's see if I add a tuning tool, I want to tune the length of the transmission line. So what I did was I first clicked the tune tool, and then I moved the mouse to the variable I want to tune, and then I click this to open up this window, all right? And now it says that I set up the transmission line electric length as 39.6 degree, and this is the nominal length, all right? But I can also change this variable from, let's say, from 10 degree to 100 degree, all right? And if we look at the results, when I change the value, you can see the impedance, input impedance changes on the Smith chart, right? And actually you can add more variables. So let's click this again and add this, the length of the shunt stub, into our tuning tool. Okay, I'm gonna tune it from 10 to 100 degree too. So now you can see we are doing a two-dimensional tuning. Okay, all right. So this gives us a hint. Actually, in a lot of practical design, instead of doing hand calculation on a graph, you actually can put the match network in a schematic without determining the true value, and then you add this tuning tool and you manually tune the value and get some matching, desirable matching. Okay, you can also try this on other circuits, like this kind of L match network. That's perfect. You can put two components, and you can use the tuning tool to tune the component value. And in real time, you can see how you can move the impedance point to the center of the Smith chart in AWR. Okay, all right. I think that's pretty much all for this demonstration. Thank you, and have a good day.